It is my distinct pleasure to introduce tonight's very special guest speaker, Dr. Edward Moses. Dr. Moses received his PhD from Cornell University and is now the director of the Fusion Science and Applications Research at the Lawrence Livermore National Laboratory in California. He has been the leader of the National Ignition Facility, the world's largest energetic laser system, and is responsible for laser technologies for homeland security, economic competitiveness, and laser fusion energy. He is now leading the effort to explore ways to commercialize laser ignition fusion energy to provide carbon-free and a virtually inexhaustible energy source for humanity. Tonight, Dr. Moses will discuss the unprecedented experimental capabilities of the National Ignition Program, its role in strategic security and fundamental science, and the pathway to achieving fusion ignition to create a clean and secure energy source. Please join me in welcoming Dr. Edward Moses.
Thank you very much. I thank you, and congratulations. It's always so great to see young people doing such great work and knowing that, the future that we have seeded will be carried on so well. So again, thank you so much. Since we're going to be talking about lasers, and I feel insecure in these kind of talks, the first thing I want to talk about is giving me another round of applause, and then we'll talk about that. So could I have another round of applause? Okay, that's enough. So I want to talk about that. Was that coherent sound or incoherent sound? Right, so let's figure this out. Next thing I want you to do is give me a round of applause, and when I say synchronize, and I don't know how you people up there in TV land are going to do, but when I say synchronize, just start clapping together without any help from anyone beside yourself. So start with a round of applause. Okay, synchronize. All right, that's enough of you. So you now know the difference between coherent light sound and incoherent light sound. And that's the difference between a laser and a light, right? In a laser, there's the feedback that exists because your ears are interpreting all the echoes that allow you to hook up and make this together. So you've made a human laser, and this is going to be something that is very important to everything I talk about. So I'm going to be talking about the National Ignition Facility and the pathway to energy security and the physics of cosmos and why they could possibly be hooked up together. So the first thing I want to talk to you about is the Lawrence Livermore National Laboratory, which is just outside of San Francisco. It's about 60 kilometers away, which takes somewhere between an hour and a week or so to get there, depending on traffic and the state of the economy. And it's about 2 kilometers square, and if you look in the corner, you see the NIF, as we call it. And it's the world's most energetic laser by about a factor of 100. And it's kind of a pretty machine. Besides that, and the trees are growing up. It's now about 4 years old since it's been operational. We started building it in '99, and here it is as it exists today. And it's the world's most energetic laser, and it's built to explore the cosmos and the future of fusion energy, and also strategic defense program. So it can do a lot of things, and the reason that's true is because, as physicists finally know, what's going on at high energy density states inside planets, inside stars, inside fusion energy systems are all identical equations, just how you tend to study them or use them, and we'll be looking at it. Now, this is not a short story, and the laser was invented in 1960 in, believe it or not, Malibu, California, right off the beach, and literally within a few days after the demonstration of the laser by Ted Maiman in Malibu at Hughes Aircraft, John Knuckles up at Lawrence Livermore Laboratory, it didn't have that name yet, it was called the Rad Lab, a socially unacceptable name at this point, but that's what it was called, realized that you could use lasers to create conditions of matter that were intense, much more intense than inside the center of the sun or most stars. And doing that, if you did the hydrogen in water, you could get reactions, not chemical reactions, but nuclear reactions that could be about 1 million times more punch. And he also realized that, at that time that, this water would be enough for any of you and your family for the rest of your lives, the amount of energy in here. And it's carbon-free. So when you think about that, that's the power. So there was a long period of time of going from that idea to the possibility of getting fusion. That means putting hydrogen together to get helium and some energy out of it, trading off mass equals mc squared in order to get more energy. And we built one laser after the other, and I was born at exactly the right time so that I could come along in around 1999 and build a NIF and take credit for the previous 50 years of work. So it was very lucky. And so we built the National Ignition Facility, or the NIF, and it's sort of a big step. It was about a factor of 60 more energy out than any other system. And that it was built not to be the biggest laser, but to be one that could make fusion happen. So what does this have to do with the cosmos? So, here's the Keck telescopes in Hawaii, and if you look up in the sky and you follow that laser pointer, actually, what do you see? And what you see is the grandeur of our universe, for sure. I mean, it's so beautiful. Who could not look at it? If you ever get up there and you can still breathe even at night without the telescope, it's unbelievable. And what are we actually seeing, though? What is it that's causing this light to come through the cosmos and go through our atmosphere and land in our eyes or land in our telescopes and see what we see? And this is the fire of fusion. So everywhere you look in the sky, either in the day when you're looking at our sun, or at the night when you're looking at stars, or what you think are stars but are really galaxies, or even clusters of galaxies, that is light from fusion. And what we're talking about now is hydrogen, the simplest nucleus, right? If you look at our periodic table on the upper left, just where everything started, that hydrogen that was produced literally 30 seconds after the Big Bang. That's where it all came out. It fell out of the energy. It's been waiting for us all this time to use, is what powers the stars and galaxies. It is the energy system of the cosmos. Every light bit you see sort of comes from that. So the question is, what is fusion? Albert told us, that fusion is when you take mass and you turn it into energy. E equals mc squared, and I know there's people here who understand this perfectly, is sort of a statement of mass and energy are interchangeable. So you can have mass, you can measure it in terms of energy, or energy in terms of mass. That's what high-energy physicists do. And the thing that's so nice about it, because the c, which is the speed of light, is so big, that c squared, which is c times c, is so big, so big, that you have very small amounts of mass can lead to very large amounts of energy. So fusion is the process of turning mass into energy. And the question is there a way we can do that on Earth? And what does this have to do with us? And, I like this picture of Albert because even though he's known for that famous equation and general relativity, one of the things he's not known for, which he deserves credit for, he actually had the idea in 1905, in his famous year, of how to build a laser. There was only one problem. He didn't notice it, and pretty much no one else noticed it for another 50 years. But his whole view of how light particles could be counted in wave-particle duality and the statistics of light was really all set up so that people could build a laser. And fortunately and unfortunately, we had to wait for a while before it was done. So I'm going to try to turn this into why that is interesting to us on Earth. Now, if you look down on our Earth in these famous satellite pictures, these are from NASA, during the day, I think something is very missing. And what is missing when you look down at it? It's us. You don't really see any signs of us during the day at this resolution. Now, you can have certain pictures that you see a lot of signs of us. You go to Google and do that, but at this resolution, we're not here. But if you look down at us at night, we're here, right? And we're shining, and we're pouring out energy, and we're burning things and making this happen. So this is a measure of who we are. And when you look at this even more carefully, we're sort of everywhere. Not everywhere, because you see some holes in this, but, it's a statement of where we're going to be, even though we're not right now. And we're really a voracious, energy-consuming species. That really is what defines civilization. We're taking energy and using it for other things besides biological functions, right? We're not just eating, right, which would what animal folk do, right? They're just sort of eating and burning calories. We really use a lot more calories than anyone else. And when you look at this, it's interesting, it's beautiful, it's terrifying. Remember, this is a picture of today. And even though it's telling you some of the story, it's not telling you all of it. It's really hard to tell looking at this, that Chinese people or Indian people are using about 1/10 as much energy as North Americans per capita. It's also hard to tell that they're growing in how they're using it, and so they're going to get brighter over time. And the fact that, unless there's a catastrophe of some sort, in the next 30 years, there's going to be about 3 billion more people joining us. And 3 billion people, just to scale it, is India and China and Europe, right? That's how many more people. And they're going to be, joining us mainly in the poor energy-starved environments. So the amount of energy we are needing is going to change dramatically. We might be at a tipping point at our planet. Some people agree with this, some people don't. This is what will play out over the next few years as we understand more about this. Greenhouse gases are rising. That's because we're burning more and more carbon. Global temperatures are rising. I think today it would be hard for me to prove that, but I think in general that's accepted. It's not always understood if there's a causality between this and this, but I think over time there'll be some more consensus on that. And this seems to matter. This famous picture of Katrina, is whether intense storms are important. Fossil fuels can affect our way of life. I was recently in Delhi, and it was unbelievable how dirty it was. I've been in Beijing, in Mexico City. I spend time in LA, which is not so bad as those places. But the whole situation that we're dealing with is in the context of a carbon using species. That's what we're doing. And it's not getting better soon. This is the population as it's growing as we speak. So I'm going to get back to why I'm talking about NIF in a second, because they are connected. What's our problem statement, I think, as humankind, which is to create safe, environmentally sustainable energy on a global scale. I think if we don't do that, our standards of living will go down. And I think that it's very obvious that there will be significant pressures in many aspects of our way of life. And I think this is the grand challenge of what we're doing. Now, why is this, just to scale this, if you look at a normal nuclear power plant or a large coal-producing plant, they put out about 1,000 megawatts of electricity, or 2,000 megawatts of thermal energy. If you look at what you need over the next 40 years to build, based on the fact that all the energy we have now is being retired during that time, and the demand will go up, we have to build the equivalent of 10,000 of those. So what are those 10,000, 1,000 megawatt plants going to be? This is about 5 times more energy than exists on Earth now. If it's coal, it could get pretty grim. There's all kinds of alternatives. We could use conventional energy sources, coal, gas, nuclear. They are there for us, if we choose to use them. Nuclear has become more controversial, not less. Coal and gas, gas is the darling of the industry now. It's slightly less carbon intensive, but how it'll play out is important. We could go to expand renewables. I think this is an interesting story, But, when people look at this carefully, it's hard to imagine that a urban population that will have 7 of the 10 billion people on Earth will live on alternative fuels. Right? It's just very hard to do that. Or we could change our lifestyle, right? We could just conserve, which is good. We could all go back to, and I don't make this as a joke, but I mean, this, conservation is a way you can do it. But it's a lifestyle change that is contradictory to the way we've been doing, or you could become more efficient, something we will do, and I think is very important for us to do, but it's, it just sort of delays the inevitable. Conservation, very intense conservation, sort of moves the curve to the right a few years, on the most optimistic estimates. So then we get back to what I want to talk about. Is there another idea? What's the source of all energy in the universe right now? It's really fusion power. In fact, if you go back to our coal, if you go back to our gas, if you go back to actually our nuclear energy, where does it all come from? We have photosynthesis. We have plants and animals living off the sun, for millions, hundreds of millions of years, billions of years, turning that energy into carbon and hydrocarbons, and that we are now harvesting. So even the energy we're using that is carbon sort of comes from this sun. But could we just get rid of that middleman, is the question. Could we just go from this to a fusion power plant on Earth? In our galaxy, we are right here, right? This is kind of an interesting thing, but our sun really defines here. And when I look at the sun, I wonder, what can you do? Now, the sun is a big ball of hot hydrogen gas. We like it because it's far away. It's, we're the Goldilocks planet, right? Not too far, so we're cold, and not too hot, not too close, so we're hot. So we're between Venus and Mercury and Mars. So we're in a nice place. And what could we do? And our sun is a fusion engine turning billions of turning mass into energy for billions of years. And it's actually burning billions of tons of hydrogen per second. It's hard to believe. Could we build a miniature sun on Earth? And I love this picture because the question is, how miniature would it have to be in order that it would be useful to us? Remember, our sun is approximately 150 million kilometers away. It's a long distance away. We have to find a really teeny one in order to make it happen. So how teeny or tiny would it have to be? Remember, our sun is 1 million miles across. You can turn it into kilometers if you want to multiply by 1.6. Puts out a huge amount of energy. It has a burning core that's around 100,000 kilometers in diameter. Believe it or not, the sun burns very slowly. It has a sort of a thermonuclear reaction per million years per particle. It has also, which I find astounding, the metabolic rate of a compost pile. But it's so big, that it gives us the energy we need. And that's really good, too, because if it had been any faster, it would have burned out a long time ago, and we wouldn't be here. Now, if you could make a sun that's a 2,000th of an inch or 100 microns, or the diameter of your hair, literally, you would have the kind of energy source you need to provide the power and energy we need. So the question is, how do you scale something that's 100,000 kilometers across to something that's 100 microns across? How do you make that the same? And is it even possible that you could imagine that the physics of the sun and the physics of something that small could be the same? And the answer is you could. Now, you might not be right, but I've dedicated a lot of my life to it. What is making the sun work? And it's gravitational, right? So what you have is this big ball of gas, and it's just crushing itself together, very slowly until you get the conditions that are needed for this fusion to happen. But as I said, it's a slow process. If we made this very small ball, we'd have to do it very fast. We'd have to find a way to squash it together without gravity, because there's no gravity to speak of in this very small part, in this very small mass, how would we get the acceleration that we needed to crush it to pressures and temperatures of hundreds of billions of atmosphere, hundreds of millions of degrees, in order to make this happen? And I think we know how to do it. And the answer is use lasers, high-power lasers, to create the conditions. What I find exciting about this idea, think about the sun. The sun is using gravity to get fusion to create light. Now, we want to run that backwards. We want to use light to create fusion to get energy. So just think about it. Is there a way to make that happen? And if you think about it, I think we can. So what's the recipe? So if you go to the recipe book for fusion energy, and you look, under Julia Childs or something, it's one of her unpublished chapters, right? It says, first of all, there's two types of hydrogen that are a little better burners than normal hydrogen. A normal hydrogen just has a proton with an electron going around it, right? There's another kind of hydrogen, and Canadians know about it, deuterium, or heavy water reactors, CANDU reactors, which is a proton and a neutron with an electron going around it, and that's deuterium for 2. But there's a third kind of hydrogen that's very exciting. It's called tritium. It has 3 nucleons, right? It has a proton, 2 neutrons with an electron going around it. So if you took the deuterium, if you study all these nuclear reactions, if you put deuterium and tritium together, it's the most easy to burn, right? And there's only one problem. The tritium doesn't last very long. The hydrogen and the deuterium that came out of the Big Bang, 13.5 billion years ago, is still hanging around and will for essentially forever. But the tritium goes away in around 13 years. So we have to figure out how to way to make that. But we can go to any glass of water again, and if you go here, 1 in 7,000 of these water molecules are heavy water. And so you can take them out one by one, and then you have to figure out how to make tritium. But if you take that deuterium and tritium and place it in a hot oven, and this is 8 million degrees centigrade, right, and compress it for a few billionths of a second, that's a not normal oven, but it's a type of pressure cooker, right, you will convert mass to energy. So that's the cookbook. Okay, but it's a tricky cookbook because, where do you get a oven that hot? Most ovens, if you turned them on that hot, would, of course, melt long before they got to that temperature. And how do you get these incredibly high pressures and for very short times? Here's how. So I'm going to show you this oven. This oven is about 1 centimeter high, and we have our hydrogen target in the middle of it. And if we look at the hydrogen target, it's a plastic wall. It's about peppercorn size, or BB shot. It's a capsule wall made out of plastic. It has frozen hydrogen in it. And what we do is take laser light and not hit the target, but we hit the oven walls. The oven now absorbs that laser energy light. It gets up to those millions of degrees in billionths of a second, and it puts out X radiation that's absorbed on the outside of that ablator, and it drives it in. And the way it drives it in, it makes a rocket. So you guys get it? And if you don't, I'll play it again. Assume you did. So here's what we're doing, right? We have an oven. We have to heat up the oven with something, which is lasers. We have our, roast or cake or turkey in there, which is our hydrogen, which is a hollow capsule tube with frozen hydrogen in it. And we're now going to heat up the oven with these lasers to millions of degrees in billionths of a second. You can see the clock running. And the energy is absorbed by that plastic. It gets real hot and it blows out. And Newton's every action has an equal and opposite reaction. So it drives the hydrogen in, believe it or not, at 400 kilometers per second. This is 1 million kilometers per hour. And you get this fusion reaction to go. But it happens in billionths of a second, and actually the fusion reaction only takes trillionths of a second. So this is a supercharged sun. We get it, it's a pulse system. It's not like our sun that stays on all the time. You just pulse it on, you get energy out, and then we have to figure out what to do with it. So how does this all work? So in real life, so this is actually a picture of a target, and you can see how the laser energy goes in, and I'll show you how to do it. Then we turn it to X-rays. It's absorbed on the walls, and then it implodes. And when it implodes, we have deuterium and tritium are put together. They make helium. That's the waste product. Not bad. And neutrons come out carrying energy. And the energy is then we can figure out a way to capture it. And if you're building a fusion energy plant, and it gets really silly at this point, you capture the energy and heat up water and make steam and turn a generator and make electricity. So we go back to basics, which is really good because all the technologies, the grids, everything we need are sitting there waiting for us. That's how big a target is, right? And if you look at that target, and this is a full-scale target, you get 40 kilowatt hours from a milligram pellet. So to give a feeling about that, 40 kilowatt hours is, sort of a week of energy for you, right? And so only a few drops of water per person per year would have the energy you need. And what's great about this energy, it has no carbon, it has nothing to do with carbon, and it's inexhaustible, literally, in the context of, I wouldn't say it as a mathematician, it's infinite, but in the context of our planet, it's inexhaustible. And you're not polluting anything when you're doing it. It's not a weapon. It's just a wonderful idea. Unfortunately, it's so wonderful, there's always a catch. It's really hard to do. But we're on the verge of doing this. In fact, we're now in a place where NIF is demonstrating the capabilities to get more energy out than we put in. Remember, our goal is to get gain. So you put laser energy in, you want more out. Now, sometimes when you say this to people, it's the free lunch, it's the something for nothing. How could you get more out than you put in? And the answer is, well, if you do the balance of you get more energy out than you put in, but you have slightly less mass, right? So you've taken away a little bit of mass in the process. In fact, a very little bit. An ounce of mass is about, 100 megawatt, 1,000 megawatt years, a power plant for a year. So it's a really interesting thought. Okay, so how does the NIF work? NIF concentrates 192 laser beams, and it's about 100 meters square, so it's a big laser, into that target. So how does that happen? Why do we like laser light so much? Going back to our coherence, laser light is so interesting because it focuses to a very small spot. Light is interesting because it doesn't have charge, so it doesn't mind getting into a very small spot. It's not like electrons or protons that have electrical charge, and the closer you put them together, the more unhappy they get about this. They just don't like to cuddle up the way light does. And also, it doesn't have mass. So, you're just carrying energy and momentum without mass or charge, and you can put it essentially into whatever size you want. There are limits that how small it will focus, but that never comes up into this conversation. So let's see how it actually works. This is the NIF control room, and this is Glenn. I'm going to show you a cartoon, then I'll show you reality. Glenn thinks he's counting down. Really, the computers are. He's just narrating. It's an electrical laser. I'll show you in real life. It's actually plugged into the wall. It's a big plug. We start out with fiber optical light. We have to go up 1 billion times in these preamplifiers, and then 1 million times more. So the gain is 1 billion million before we get to the laser. So this is a chunk of light. It's around 6 meters long. That's 20 billionths of a second. And it's going back and forth. It goes, of course, much faster. This is slowed down. and it really doesn't play music, I have to tell you. That was a very hard problem, though, getting it to go the speed of sound and the speed of light to be the same. But anyway, so we got this going. So that's 8 beams. That's a unit cell. That's the Lego block. So we're now going to look at 48 beams. That's one cluster of beams. And then to its right, in a bay, we see 96 beams. And now we go from 2 dimensions to 3. Remember the geometry of a target. And now we're going to look at the bottom side. The beams are coming from the other side. We're now wrapping around, so now we have that cylindrical geometry. Now we're going to turn the light blue. I'll talk about that in a second. And now we're in the target. So the first microsecond has gone by. Now we're going to slow down that clock again. This is real, by the way, even though it's a cartoon. We watch, you're experts at this now. The light is going in. It's heating up the oven walls. It's now putting X-rays onto the target. The target is getting hot and expanding, driving in the hydrogen. And, either we're famous or infamous at this point. So we do this every day, so we have been. And there's been around 1,500 shots on the NIF, not all of them for fusion, but for other missions too, basic science missions and other missions. But this is how it looks. And but the question people have is this real? That's just cartoon. So of course, since I'm a project kind of guy, I always want to start with dirt. At one point it was just a hole in the ground, and this was an El Nino year. And I have to tell you, 3 days after this, it wasn't a hole in the ground; it was a pond. But we did dig out from that, and then this is how NIF looked like when we were building it, from the outside, and then this is how a laser bay looks like before you put lasers in it, and you can see from the scale size of these livermorons up there on the upper left, they're normal-sized people, so you can see it's about 100 meters long and about 40 meters across and about 20 meters high. And this is one of the 2 laser bays, and this is how it looks today, with the lasers in it. And you can see, with those beams are 4 by 2 high. That was that unit cell that we saw. And if you look at it from above, and by the way, you're all welcome to come to the NIF. And I hope if you're in the Bay Area, you let us know. You can just go to the Lawrence Livermore website and arrange tours. You have to remember to bring your passport. I won't tell you what happened to me yesterday when I didn't have my passport. But anyway, I got in. Anyway, this is how it looks, and this is, the 96 beams. This is another set of it. And these are the laser power supplies, and this looks kind of cool, but this is where the energy comes off the grid that we stored up to, put it into the laser. These are sort of battery packs, right? And this is the preamplifiers, which I think are beautiful, and you can see how they come together, over and over again. And this is just art, but this is another view of the preamplifiers. And this is some of the laser diagnostics that we have. And, when I go to the NIF, I'm sort of stunned by it in many ways, because it's sort of, to me, it's functional, it's beautiful, and it has an incredible potential mission. And this is what a target looks like, actually, in the target chamber. And so you see that little target. And this is what some of the glass looks like. This is how it looked like when we were building it. And I also find this amazing. And this is what that looked like a few months later. And this is what the target chamber looked like when it was coming together. This is made out of aluminum. And just, to tell you, people always say, well, why is it aluminum? They say, well, it would be easier to put in place. Well, that's true. But the real reason is when neutrons come out, you don't want it to activate. This looks like, for these neutrons, this sort of looks like a very clear piece of glass for light. They just go right through it without interacting with it. And this is how a target chamber looks when it was being rigged into place. And this is how it looks when it went into that place. And this is how it looks today. When you look at this picture, I think it's really interesting, because you remember what a target looks like? A ball with laser light coming in, except the ball is 2 millimeters across. This is a ball with laser light coming in, except it's 10 meters across. So actually the building is, a very large scale size version of the target, or vice versa. But we built the entire building around the geometry of the target. So that actually is a great organizing principle when you're putting something together. It simplifies the concept in your mind and it makes it really easy to operate too. This is how it looks like inside that target chamber. So this is one scale. You can see humans over here, and up there. But this is how it looks like when you're inside, and this is how it looks like now, right? And you can see where the target is. If you look, right, and I know it's hard to see this, but right in the center, that's where the target is. And people say, well, why do you need such a big target chamber for such a little target? And the answer is there's two reasons. One is the, F number of the optics in the target. You have to sort of have a distance and for the aperture so that it works optically. But the other is it puts out so much energy that you can't have the walls of the target chamber too close because the energy that comes out will actually spall off the inside of the wall. So you sort of have to get away about 5 meters. But you can see diagnostics in it and the like. Now, I think another thing that's interesting, for those of you who are into stealth technology, if you look at the target chamber when we first put it in, it was all shiny, right? And if you look at it now, it's all dark. And we put Venetian blinds inside of it so that light couldn't reflect around. But what do you think those Venetian blinds are made out of? Well, they're shiny steel, right? But they're all set at angles so nothing reflects back, right? So no matter where you look, it's dark, and therefore this keeps light from rattling around inside it. And that's a very important thing for functionality. So there's the ignition target, and like we know where we are in our world is defined by the sun, right? This is where we are in our world. In NIF, it's defined by where the target, we call, ITS, the Integrated Target System, or it's the target stupid, hit the target, right? And the target, we hit it to within 30 microns, all the beams, that's about 1/3 or one half the diameter of your hair, and within a few trillionths of a second. So not a millionth or a billionth, but a trillionth of a second. So it's an extremely precision machine. And I think that's important. This doesn't work. Remember I said this was hard? It has to be energetic, it has to be powerful, and it has to be very precise in order to make this happen. Now remember we talked about the light started out as infrared and at the very last second we turned it into ultraviolet? Believe it or not, we use these crystals, these magical crystals called potassium dihydrogen phosphate. Actually, this is what I wrote my thesis on, except when I was growing them, they were the size of the end of my pinky, right? A small finger here. And, this is now considered a small crystal. It's an interesting crystal because those of you who have ever made rock candy, using sugar, for your kids or something like that, this is a water-soluble crystal. Potassium dihydrogen phosphate, if you're a gardener, is a very familiar fertilizer, right? So if you were to pour water on it, it would melt, and then you could put it on, especially your roses, they would grow very well. We wouldn't be very happy. But this takes about 2 months to grow a crystal like this. And it's truly a single crystal, and what's very interesting about it, if you cut it into plates about a centimeter thick and about 40 centimeters by 40 centimeters at very specific angles, you can put infrared light into it, and pure infrared light, and green light will come out. It's not like a prism where it's just spreading light. It changes the color of the light. And it's a harmonic generator. And then if you take the green light and the little leftover infrared light, you add those together in another crystal, it comes out ultraviolet. It's sort of like tuning a piano, right? If you add these frequencies together. So we do this, and people say, well, how efficient is that? And we can get about 80% conversion of infrared into ultraviolet, which is just amazing to me. This is some of the optics to give the scale of the beams. People think of laser beams as small and round, like this. Can you see this sucker here? I don't know if you can. But these beams are around 40 centimeters on a side, and they're square. And that's because they carry so much energy. If you made them any smaller, they'd literally destroy their own optics. And, it all works. This laser works. It's a 2 megajoule laser, 2 megajoule class laser. The biggest laser that's operating besides this is around 20 kilojoules. But we didn't build it to be big. We built it to do fusion, right? In fact, this is the smallest, biggest laser we could build that we had confidence would work, right? So we weren't trying to make it big. We were trying to make it as small as possible, and it would still work. And it is working. And, the yields have increased, and I have to say this, if you look at the yield, most people don't count in, millions of billions, but those are millions of billions of neutrons, which is not a tremendous amount on one sense, but the thing that's so interesting about this now, we have yields that are at the point that we're getting as much energy out, in fact, more energy out, than the work we've done on the hotspot, right? So as a physicist, you just remember this is sort of like a piston, right? You're driving it in with this X-rays from the laser, and it's getting compressed and compressed, and it's pressure times the change in volume. That's how much work you do. It's sort of like a diesel engine, right? And at some point, you do enough work that you get it hot enough that it'll start to burn. And then if you do that just right, you'll get more energy out than you put in. And we are now at that point. Now, from the point of view of getting more energy out from what we put in from the laser, we're not there yet. But it's an interesting place, like an engine. It's a threshold process. At some point, the temperature gets high enough, and the conditions are right so that you have a propagating burn, and it propagates, this energy burn into the entire tiny mass and starts turning energy into mass for around a quarter of the target. When that happens, this will go up another 3 orders of magnitude. So you go up to 10 to the 18th. So you go from millions of billions, right, to billions of billions, to trillions of billions. And we're sort of working up that chart, and you can see how it's going. You can see it was a little bit rough in the beginning when we were turning on the system, and this is sort of chronologically. But, now we're sort of on the path, and, it's sort of like tuning up an engine. Trouble with this engine, we were the first ones who ever turned it on, right? So it's not like someone has given you an instruction manual and you're just, tuning it up. We think ignition will be a defining moment in the world's energy future. That's a bold statement, but if you do have ignition, the question is, can you make it practical, right? Because it's one thing to talk physics, and it's another thing to talk, real life, bringing it into the marketplace. And to get it into the marketplace, you have to think about what is it, the attributes of a system that would bring significant carbon-free energy for humankind, and hopefully forever. We don't see a source other than this. In the long run, I believe most thinkers, do not have another idea for the big story, right? How hard it will be. Our National Academy of Sciences looked into it. Is this an idea that's worth looking at? And I'll show you how you would do it. And we were very happy to say, after a 2-year study, they came that there's a compelling rationale to establish inertial fusion energy program in the United States to look at this, that the external reviews are very confident that we will get, fusion burn, and significant gain on the NIF. And we should be looking to see how to make this happen. Because NIF is the performance proof of principle for an engine. This is an affirmation of our vision. What is our vision? We go from NIF, which is a physics machine, right, to an initial life plant. Life is laser inertial fusion energy, or a laser inertial fusion engine, and we'll talk about why it's an engine, because right now, remember, NIF is a pulsed process. You do one shot, then you come back a day later or a week later and do another one. How would you turn that into, like your car, 800 RPM? If you had an 800 RPM NIF, you would have 2,000 megawatts of thermal energy, which if you chose to make electricity out of it, be 1,000 megawatts. Or if you wanted to do other things like, make water, desalinate water, you could do huge amounts. Or if we talk to people in Edmonton about things you could do to take the sort of footprint of carbon in the oil sands, as they're now called, and make them cleaner. This would be a way to do it. And this is what a fusion engine plant would look like. And it's kind of interesting to me because if you remember, the target chamber is built around the target, and we have that long laser hanging off of it. Now, that laser is, even though it's the coolest laser on Earth, it was conceived of in the 90s, right? And when you're building big projects, you have to, fish or cut bait. You have to decide what you're doing. You can't say, well, 20 years from now we'll have better technology, so we'll wait. You just finally have to do it. But it is it was an old laser. It only runs about once every 90 minutes without it overheating. So what do we need to look at an 800 RPM system? What we have is, if you look at it, these very small lasers. I'll show you a picture of them. We've shrunk these lasers a factor of 10, just like your TV set used to be long, deep, now it's thin. And now we would have a boiler, and we would fire in targets, and they would light off, right, one after another, and then we would just keep doing that. And now people go, well, what's wrong with that? And that, by the way, that's 800 RPM. So if you want to know, if you don't anyone have any problems here, but you would just fire them in, and the energy would come out. And what's amazing is, how do you collect it? Well, what you would collect it is, if you look at this, it's just a boiler, right? So you would have pipes, around it. And what will be the thing that would be interesting as the pipes? The pipes have to absorb neutrons. Neutrons tend to go through everything. They don't stop. They don't have charge. They just go. But there's certain materials, like lithium, that really have good stopping power for neutrons. And there's something very interesting about lithium. It's a good thermal material, so it has good heat capacity. And it has fairly low melting point, and so you could absorb these neutrons in the lithium, and in pipes that are only 10 centimeters across, and just pump it out of there, and pass the heat exchanger and boil water or heat up another gas to make electricity. But there's something else very special about lithium. When a neutron goes into lithium, what does it make? The one thing we don't have, tritium. So lithium plus a neutron makes tritium. So this would be like driving your car down the street and it was making its own gasoline, right? So not only is it making thermal energy, but it's making the fuel that you don't have in order to run it. So, and you can make more fuel than you use. And not only that, that reaction is exothermic. So when you're making lithium plus neutrons to get tritium, you get about 20% more energy about. Now, when you get those combinations of things, you just don't call it luck. You just call it, you got to do it, right? So that's what you have here. But I think it's really important to look at this as, a very simple architecture. You've seen it in NIF. We just expanded out one more size to take the lasers we have, which are around 100 meters long, make it 10 meters long. Again, to say this, your TV set, your cathode ray TV set, used to be like this. Now it's actually, a few hundred microns thick. They put a frame around it to hold it and to keep it from folding up. And we're doing the same thing with these lasers. We're using laser diodes instead of flash lamps, and that's how we can do it. So when we were talking about this engine, when we were designing it and thinking about this concept, one of the most important things was that it's based directly on NIF performance. We don't want something, that old joke, when will there be fusion energy? It'll be in 50 years, whatever year you ask, right? The question is there a way to get a 10-year horizon to go from proof of fusion performance to proof of energy production in a commercial manner? That's sort of a controversial statement. A lot of people think that's a little bit far out. But if you look at the design principles we have, it has to be based directly on NIF performance, which this is built around. It has to use available technologies and materials, so you can't have unobtainium or something that will be invented in 30 years. You have to be able to buy it today. But we also admit that it might not be the cost you need today. You have to have it, but you have to have a path to cost. And like the lasers going from where we are now to the laser diodes really follow Moore's law kind of thing. So you can project ahead on these pretty nicely, and most people agree. You have to have a systems engineering approach so that when you go to utilities, which we have, they don't ask you about the physics. They ask you, will it operate, and how much will it cost to operate, and how do you manage operating it? And it has to be modular, factory built. And if it was sort of built in place, you really would want plants that were building lasers, building target shooters, building this stuff and hooking it together. And it has to be something you could license. It has to be attractive safety basis. Finally, no matter what I've learned, and I think everyone has learned, the public has to buy in, right? If the public doesn't buy in the end, it doesn't happen. And so you have to be very sensitive to this, education, honest communications, and an approach that you could do this. We think we've done this. We've talked to a lot of people in the sustainable environment community, the environmental community, the power producing community, the power using community, agribusiness and the like. And, they sort of like the idea, they see it. And it sort of answers a lot of questions. It's carbon dioxide free. It's actually methane free too, which is not a minor thing. The fuel is abundant and everyone can have it. There's no place that doesn't have this much water, literally. It's negligible toxic emissions. It's compact land use. This is about 100 meters across, and you would build the plant on something that's a kilometer square, which is, a place like Canada, there's a lot of that. It's very minimal in water use. In fact, you could get rid of, for some places, the whole idea of running running the cooling system off of water. You could run it off of air under the right conditions. It costs you a few percent in energy, but that's sort of important, and it's safe. There's no way that it's hard enough to make it happen. It's not going to happen on its own. It's not like a fission system, where once you have enriched fuel, there's always the possibility, even though I think with modern reactors, unlikely that something bad will happen. But in this case, it can't. The worst thing that can happen here is nothing happens. So if you fire at it and somehow you miss the target, well, you missed the target, right? There's nothing that can happen spontaneously. The applications are clean electricity, clean water, fuels, process heat. Process heat is a really important issue, again, for the oil sands and other people who are interested in fertilizer production, things like that. Because you have really high quality heat that you can use for electricity, and then you can use the bottom of the heat cycle for whatever you would want to do. It's a nice idea. And this is a U.S. example, but it has, we've had this group called the Oxford Economics Group look at it from the point of view of jobs. And, in the United States, if you captured a quarter of the market in the next 30 years, it would be bigger than the aircraft manufacturing industry or machine shops or semiconductor industry. So there's a lot there, and the kind of jobs you would have everything from high technology jobs, to crafts and construction jobs. So it's really broadly across the environment. In order to do this, and I know we're at the Perimeter Institute, but this goes back to the real issue. Physicists think, that the issue is science. Well, that's the prerequisite, right? That the science is right. But getting, these communities all together around this so that they would do it is really what we've learned in this global, we're all learning in the global community is what you have to do. So I think this is an important, very important point of view. I do want to say this didn't come easy. The NIF represents around a $5 billion investment by the U.S. government. But we've developed 3,000 vendors, partners, and even though I don't show the Canadians, there's about 100 here. This is something for another audience. But anyway, there's 100 Canadian partners, and it's growing. And this is Team NIF. There's a lot of people working. So when you think about going back to Albert and our cosmos, right? And you think about where all of our energy is coming from, if we could just capture that physical process, and at the scale of, a BB shot that when it's burning is the diameter of your hair, and you had a technology engine to drive it, which we think exists, from the point of view of laser technology, target technology, balance of plant technologies, and you could put it together, it looks like a story that could work. Now, I want you to know, I'm dedicated to this idea. I ran the NIF, and now I'm doing this, because I really think that this is the next step for this process. There's a lot of people have put a lot of energy into it, and still, and I pardon the pun, still do. Now you can see this picture. That joke. I did all of this, and all I got for it was a T-shirt. So this crowd. If you saw the last Star Trek, I don't know if you have, Into Darkness. It was filmed in NIF. So if you want to see NIF with better lighting than exists, if you came to it, you could go watch that movie. They gave us a T-shirt. So anyway, we're not the only ones who are doing this. The United States right now is the leaders in this. But the Chinese are following. They're building a laser called Shangguan, or Divine Light, sort of a better name. But the French are building laser megajoule, so that's another laser. The Russians have announced they're building a NIF-like facility. The Brits work with us. They have a smaller version, but it's operational. And the Japanese and Koreans are working on the technologies associated with this. This is sort of a bigger international effort than people are generally aware of. And, we work with people, particularly in Alberta, in their physics departments and in their potential application department, that makes this very exciting as I think of as a North American, activity. So this is something that's going on internationally, and I think this is, besides, National Academy of Sciences points of view, an affirmation of the potential of doing this. People are investing in it. The fire fusion powers the stars and the galaxies. I think this is what draws me to this. I think there's proof of principle on a big scale, right? And I think the question, could fusion power our planet? So if we look down there, and it was brighter, better, and cleaner, would be very important to all of us in the long run. And today we live on hydrocarbons, so here's a tanker coming out of the Gulf, right? But if you look at it the other way, we just use that water. Tomorrow we live on life, and that tanker goes away. It's the fuel in that case is the ocean that we live in. Okay, so thank you very much. That's the story. that I would like to tell. That was my time.
That's perfect. That's perfect. Very good. You can take the questions right out there. All right, we'll open the microphone to if anyone who has any questions. Also, the Twitter feed, if you want to send a question from the other rooms, that's allowed as well. And a note to those that didn't make it into the theater, Dr. Moses has offered to spend lots of time in the atrium to talk after, so you'll at least get a chance to see him in person. So, as we're waiting for questions to come up, I have a question. It's sort of two-parter. Part one is, what was the path that led you to building such a facility personally? How did you get there? And then B, how terrified were you to be in charge of building such a facility?
Well, the path that I have, it's kind of interesting. It starts when I was about one, apparently my first word besides mama and papa was light. I was intrigued by it. But I grew up in construction, and then I became an engineer, and then, I became, physics oriented. And, but the fact of the matter is I was always interested in building stuff. And when I was a sophomore, is it ringing right now?
Just a little.
Yeah, so when I was a sophomore, I saw a laser for the first time, and in those days, a laser was big and clumsy, and the power supply, was large, it weighed half a ton. But I saw that laser light across the room, that small spot, like this, over here. And I just couldn't believe it. And, I knew I was going to follow that beam of light wherever it went. And, I went off and did, research in lasers, and then I, went to use aircraft where the laser was invented and did work there. And then I went to the lab and worked in atomic vapor laser isotope separation. And then I did it in a variety of ways. And I was just finally drawn back to NIF. And the question is how terrified was I? I never was terrified. Big projects like this are really interesting because there's so many possible ways to succeed. There's a few ways to fail, but there's so many ways to succeed, and I always thought about it that way. If it's never a straight line. It's like a sort of a Feynman integral. There's thousands and thousands of ways to get through. The problem is as long as you keep your eye on where you're going. Had a great team. You don't do this alone, and it was just so irresistible. So I never felt terror. I probably should have, but I just felt it was a great opportunity.
Well, that's great. If you do have questions, make your way to the microphone and you can ask. And I have a second question that did come from the Twitter feed, and it's related to what I asked you earlier today as well, which was, so more energy out than in. And so you touched on it. Maybe you want to highlight that again. To a physicist, yes. To a politician, no.
No, politicians get that. No, so the story on more energy out than in, right? If you start with a certain amount of mass and a certain amount of laser energy in, right, and you convert some of that mass to energy, you can look at you can measure both in terms of energy or mass. Say you measure the laser energy in terms of energy and the mass in terms of energy. And then you look at the mass that you have left in terms of energy and the energy you get out, you can get more energy out than you get in. But both sides of the equation balance. It just has to work. And, you can do it, and it's going on in the sun all the time, right? And it's going on in every star all the time. And the whole idea is to make it happen here. So, you're trading off the mass you have and trading it for energy. So, the energy you put in is converted to mass. If you add them up both sides, you're fine.
Pratik?
First of all, thanks very much for a very interesting and inspirational lecture. Just a quick question. I'm curious as to, aside from the inertial laser method of triggering fusion, are there other potential methods that are being explored to get to the same point of fusion energy?
Yeah, so there are. So there's the first way is the big way, right? Gravity. That's what the universe works on. It just crushes gas together until it reaches those conditions. Inertial fusion energy is, the one that's the version of a gravitational system, except instead of accelerating by the force of gravity, you accelerate with this rocket, this laser-driven rocket. So that's sort of that story, except it burns much higher pressures, much higher temperatures, so it burns off the fuel in a very short period of time. Another way to do it is at low densities, and this is magnetic confinement fusion. So if you had something that, where you could have a magnetically confined bottle of plasma and heat up the plasma at low density, it could burn, and it's sort of between the picoseconds that a laser happens at and the million years that the sun happens. You could do this over minutes. You have a pulse system. And there's a project in Europe called ITER. It's in France, and it's a coalition of several countries trying to put that together. That should be operational in 2025 to 2030, and it's a way to do it. There's other ideas that people have that come and go. Most of them don't stand the test of scientific peer review in time, like cold fusion, things like that. They just really don't hold up. So if you really think about the things that people are talking about, is inertial confinement fusion on Earth. We can't do gravity, and magnetic fusion.
Next question, please.
Before you had mentioned scales for the lasers, and I was wondering, could it be physically possible to scale it down to a level where you could run, say, a cruise line ship or a tanker?
Yeah, so this is also, this is a very good question. What makes the system big, right? And, the thing that makes the system big is, if you get a certain amount of energy out of the target, and say the word is, 200 megajoules per shot, people don't normally think about megajoules that way, but 60 kilowatt hours per shot, right? You sort of get to that sort of forces you to a certain size, 10-meter size target chamber. Otherwise, it'll be sort of damaged by the process of the explosion, right? And then you have to think about, well, now I have all those neutrons, I have to make sure everyone's safe, so I have to put shielding around it. And then I have to put a laser around it. And so when you go to that scale, you sort of get to this larger scale. Then you say, well, can I just run it at lower energy? Well, you could. You could say, I'll just not have as much rep rate. Instead of doing it 10 times a second, I'll do it 1 time a second. The flaw in that thinking is you're still that shot. When the shot goes off, it has so much energy. You have to be back off so far. You still have to have shielding because it's a single shot device. So when people talk about, is there a way to make a smaller system that you could put on a ship or not, people haven't come up with what I think is a valid concept. On the other hand, if you think about smaller places like in 250,000 people somewhere, and you want to have off the grid or small grid systems, there's a lot of ideas about how to do that.
Thank you. Another question?
Yeah, I think we're all really excited to be watching the birth of a new industry. I look forward to one day having a fusion reactor power my smartphone. No, really, I hope to be alive for that. But there were also some comments in the intro to today's lecture about fundamental research being done at NIF into high energy states of matter. Do you have any comments on that?
Yeah, I talked about that today. I gave a talk in the Perimeter Institute today. I could go over that. So the thing is that you have to think about is when you look up into the sky and I say it's a fusion burning engine, right? Okay, it is. You look at that, but it's a lot more than that. We're kind of the universe is either empty or it has this mysterious dark matter and energy. I'll forget that stuff for now. It's just sort of a vacuum or low energy state. or it has high energy density matter, which are stars, and the like. We're just sort of not really serious contenders, except, here in the mass. So the question is, could you study states of matter, stellar systems, planetary systems? Can you study things like how matter and antimatter, finally decided which way they were going to go at the time of the Big Bang? And the answer is you can. When you put these matter at extreme conditions, if you're talking about billions of atmospheres, high temperatures, or actually low temperatures, very high pressures, you can do that. We've actually been to the center of Saturn, so we've taken, matter and taken it to the center of Saturn and, showed that, if you could get there and get out, you would have gigatons, billions of tons of diamonds. We're going to go to the center of Jupiter pretty soon. Not, I don't mean actually to the center, but material, create conditions. We've been to the center of the Earth and showed that how iron acts at the center of the Earth is very different than it acts now in terms of its strength and other properties. And so these things are fundamental physics issues that we are studying. And we're doing this, with universities around the world. So basic science is a very important part of all that we're doing.
So just before we go to the microphone, I have to honor my request to the Twitter feed. Here's the question: why doesn't the laser melt the gold before it has a chance to start fusion?
Yeah, actually, it is a good question. The word melt is an interesting word. The melting time period is, it's going up to millions of degrees. Gold is melting at thousands, right? So it actually it just goes through that period instantly, essentially. So what happens is, you're heating the gold to very high temperatures and it becomes a plasma, quickly. So the whole idea of thinking about this as, a solid gold oven is, which is how I probably described it, is not very useful, very short periods of time after it begins. The reason we like gold or lead or, other types of materials like that is they really have a lot of electrons in them, and the electrons will, interact with X-rays and sort of keep them in the hohlraum, whether they're in the solid condition or the plasma condition. So it's a good question. It doesn't quote unquote melt. It goes into a plasma state, which is, gold ions and electrons essentially instantly.
And our last question.
Just out of curiosity, I was wondering, has there been any effort to use like ultraviolet light instead of violet light, or is it just impossible to see it, so it makes it difficult to use it as an alternative?
Okay, so the word ultraviolet and violet, so this light is 350 nanometers. We call it ultraviolet. It's not deep ultraviolet, but it's certainly not visible. And it's a very good question. I mean, if you could go further into the blue, or shorter wavelengths, higher frequencies, the laser plasma interactions, which are sort of a problem that we have. When the laser light, ionizes this gold and ionizes this plastic, right? You now have this soup of conducting electrons and ions. Now, the thing that's wrong with that is, it tends to reflect light and do other things with it. It's kind of disappointing if you put all your energy in and it comes right back at you, right? And so, going to the ultraviolet tends to mitigate against those factors. So the question is, could you go further into the ultraviolet and do better? And the answer is, it gets hard because, there's not a lot of materials that transmit ultraviolet light without absorption, and if they absorb, they damage, and therefore it's not a useful thing. People talk about going another 25% further into the blue. At that point, everything is sort of getting black, and so there's no really good way to do that. But it's a very good question, and it's debated hotly all the time. Could you go more to the green because then lasers are easier to build? Could you go more to the blue because the plasma will be easier to control? And 350 nanometers, which is 3 times the frequency or 1/3 the wavelength of the fundamental seems to be a very good place to be. And we've conquered the damage problem at that point.
Ladies and gentlemen, Dr. Edward Moses.
Thank you very much.
Thank you. You can go.